All right, welcome to our first lesson on outcome 30.06, which is the counting methods. And the first one is the fundamental counting principle. So we're going to take a look at our first example. It says Aiden is choosing his outfit for a Foundations 30 class. He really wants to look dapper. He has 3 pairs of pants, 4 pairs of socks, and 2 shirts to choose from. How many different outfits can he wear to school if he must wear a pair of pants, a pair of socks, and a shirt? Okay, so we want to figure out if he needs to wear a pair of pants, a pair of socks, and a shirt. Okay, so basically he has 3 pairs of pants. So we could go, okay, I've got pants 1, pants 2, pants 3. And then he has 4 pairs of socks, right? So he's got 4 options for socks coming off of each pair of pants. So 1, 2, 3, 4, sock 1, 2, 3, 4, same thing there. And then for each of those, he has 2 shirts that he could choose. So shirt 1, shirt 2, that's a lot of branches on my tree, but basically kind of every branch that I have represents an outfit, right? So I could have 1, 2, 3, 4, 5, 6, 7, 8, and then it would be another 8 and then another 8, right? Because there's 8 in each branch. So 8 here and another 8 here and another 8 here. So that's a total of 24 possible outfits that he could wear. Okay. How many different 3-digit numbers can be formed from the digits 2, 5, 7, 8, and 9 if the digits may not be repeated in the same number? Okay, so I need to make a 3-digit number. And I'm choosing from 5 possible digits. So basically, I could have 5 choices there, right? And then I could have whatever's, and then I could have 4 choices and then 3 choices. So like if I had the number 2, I could have 2, and then the next digit could be a 5 or a 7 or an 8 or a 9. And then if I've used the 2 and the 5 already, this could be a 7, 8, or 9. This 7 could be a 5, an 8, or 9. This could be a 5, a 7, 9, and this could be 5, 7, or 8, right? So I've got, if we count them all up, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For each of these, it would be 12, and then 12, and then 12, and then 12, and then 12. Okay, so that would be a total of 60 altogether. So 12 times 5 would be 60 different outfits. Okay, and I kind of alluded to it over here, but we have something called the fundamental counting principle, where basically it says if I have to make n decisions, like a certain number of decisions, in the first decision in A ways, and then the second in B ways, the third in C ways. So if I use this as my example, I had to make 3 decisions. So I set up 3 blanks. The first one I had 5 choices to make because I had 5 numbers to pick for that first one. And then the second one I had 4 and then 3 because I could not repeat the same number. Okay, then what I do is I multiply those together. So when we did our tree diagram here, we got 60. If I also do 5 times 4 times 3, I also get 60. Okay, so that's called the fundamental counting principle. So let's just try and do these otherwise a little bit shorter. So a small restaurant lists 3 appetizers, 7 main courses, 4 desserts, and 6 beverages. How many different ways can one order a meal that consists of 1 item from each category? So essentially, I'm going to make 4 decisions because I got to pick an appetizer, a main course, a dessert, and a beverage, and I'm going to multiply those all together. So if this is my appetizer, this is my main course, this is my dessert, this is my beverage. I have 3 appetizers, 7 mains, 4 desserts, and 6 beverages to choose from. So when I calculate that, I take 3 times 7 times 4 times 6, and I end up with 504 different meals that I could pick from. Okay? How many positive 5-digit integers can be formed if repetition is allowed? So it's not telling you the group that you can choose from. So the digits that I have to choose from are the numbers 0 to 9, right? So it needs to be a 5-digit integer. So there's 5 spots, 1, 2, 3, 4, 5. I can't put a 0 in the first spot because then it would not be a 5-digit integer. So there are 10 choices, the numbers 0 to 9, but that first one cannot be a 0. So there's going to only be 9 choices there. It can be anything but a 0. And then the next one, I could put a 0 in, or a 1, a 2, a 3, a 4, a 5, or a 6. Repetition can be allowed, so I'm going to have 10 choices for that one, and then 10, and then 10, and then 10. So that is going to end up being 90,000 different integers that I could make. If there's no repetition allowed, so I go back to my same 5 choices that I have to make, again, 9 in the first spot. Now, whatever I chose there, there would be 9 in the second because I can now choose my 0 plus whatever's left, and then 8, and then 7, and then 6. So 9 times 9 times 8 times 7 times 6 is 27,216 different choices. Okay, let's just look at another couple of examples. So how many different 4-letter arrangements can be made that satisfy the conditions where no repetition is allowed? Okay, and it must begin and end with a vowel. So I'm doing a 4-letter arrangement, so I need 4 choices, and I have to begin and end with a vowel. So my vowels are A, E, I, O, and U. So I have 1, 2, 3, 4, 5 vowels. So I have 5 choices here, and there's no repetition allowed, so then I can only use 4 choices there. Then we know that there are 26 letters in the alphabet, so 5 of them are vowels, 21 are consonants, however you spell that. Okay, so I'm going to have 21 choices here because it can't be a vowel. Actually, it doesn't say that it can't be a vowel, so we actually would have 24 choices there because I'd have 3 vowels left, and then the other 21, and then 23. So 5 times 24 times 23 times 4 is 11,040. They have to have a vowel in the even and a consonant in the odd. Okay, so consonants, odds are the first and third position, so I'd have 21 and then 20 because I can't have repetition, and 5 and 4. So 21 times 5 times 20 times 4 is 8,400. If I don't have any vowels, so that means I have 21, 20, 19, and 18. That is 143,640. And if you have no consonants, well, that's going to be all vowels. So 5, 4, 3, 2. And then multiply all of those together. And that gives me 120. Okay, picking from the digits only of 1, 2, 4, 5, 7, and 8. And we can have repetition. So I'm making a 2-digit integer. How many positive 2-digit integers can be formed? So just nothing crazy here, just any 2 numbers. So 1, 2, 3, 4, 5. There are 6 of them to choose from. So I've got 6. Because repetition is allowed, I could have the number 55 or 77. So I've got 6 choices there. So that is 36. How many positive odd 2 digits? Well, if it's going to be odd, it must end in an odd number. So it has to end in 5 or 7. So I've got just 2 choices there. And then it can be any other number. So I've got 6 choices there. So that's going to be 12. How many positive even 3-digit integers can be formed? So if it's going to be even, it's going to end in 2, 4, or 8. So there's going to be 3 choices, and then it can be anything. So this is going to be 108. I just need to go back up here to my B. I just realized a mistake because I've got actually 3 odd. I've got 1, 5, and 7. So this should actually be 6 times 3, which will give you 18. 3-digit integers larger than 500. So if it's larger than 500, it means that this digit here has to be a 5, a 7, or an 8, because if it was a 4, it'd be like 400 and something. So I've got 3 choices there, and then these can be anything. So 3 times 6 times 6 is 108. Okay, so you can go ahead and practice some of these. You just have to read them carefully, set out your number of decisions to make, and then multiply together.